Every time you move, think, or even just breathe, you are spending a currency you can't see, earn, or print more of. But what are you actually spending? It's not money, and it's not time. It's something that flows through everything you do, and once it's gone from one place, it has to show up somewhere else. In this video, we're going to uncover what energy really is, meet its two most important forms, learn the one rule it never breaks, and see how that rule powers every chemical reaction in the universe. It's a short journey from a bouncing ball to the fire in a candle, and by the end, you'll see the world a little differently. Energy is the capacity to do work or transfer heat. Think of it as a universal currency. Just like money lets you buy things or pay for services, energy is what lets you lift a book, warm your hands, or make a car move. And just like money, it's a conserved quantity. The total amount in a closed system never changes. It doesn't get used up, it just moves around or changes form. So when you feel tired after running, you haven't destroyed energy, you've just transferred it from your muscles to the ground and the air. Energy comes in two main flavors. Kinetic energy is the energy of motion, a rolling ball, a flying bird, the vibrating atoms in a hot cup of tea. Potential energy is stored energy, waiting to be released, like a ball held high above the ground, or a stretched spring. Imagine a bouncing ball. At the top of its bounce, it has lots of potential energy because of its height, but almost no kinetic energy because it's momentarily still. As it falls, that potential energy turns into kinetic energy, making it speed up. At the ground, it's all kinetic, and then it squashes, storing energy in its own springiness before bouncing back up. It's a constant dance between the two. The rule that governs all of this is the first law of thermodynamics. It says energy cannot be created or destroyed, only transferred or transformed. Picture a simple ball attached to a spring. When you pull the ball back, you do work on it, transferring energy from your muscles into the spring as potential energy. Let go, and that potential energy transforms into kinetic energy as the ball moves. It then compresses the spring on the other side, turning kinetic back into potential. The energy never disappears, it just changes its address. In a perfect world with no friction, this back and forth would go on forever, with the total energy staying exactly the same. All chemical reactions are just rearrangements of energy. Take combustion, like a candle burning. The wax molecules have potential energy stored in their chemical bonds. When you light the wick, you provide a little activation energy to break some bonds. The atoms then rearrange into new molecules, carbon dioxide and water, with stronger, lower energy bonds. The extra energy that was stored in the original bonds is released as heat and light. The total energy before and after is exactly the same, it has just changed form, from chemical potential to thermal and radiant. So the whole idea is, energy is the universe's unbreakable accounting system, and chemistry is the art of moving it around. If you touch a beaker where fuel is burning, it burns you. But if you touch a beaker where ice is melting, it just feels cold. The chemicals are doing opposite things with energy, and you already know the difference. One is sending energy out, the other is pulling energy in. We're going to meet the three characters in every energy story: the system, the surroundings, and the universe. Then we'll see the two ways energy can flow, out or in, and why that tells you if things get hot or cold. Finally, we'll dodge a common mistake that tricks a lot of beginners. Imagine a beaker on a lab bench. The stuff we care about, the reacting chemicals inside, that's our system. Everything else is the surroundings, the glass beaker itself, the air, the table, your hand if you touch it. Add them together and you get the universe, at least for this experiment. The first law of thermodynamics tells us the total energy of this universe never changes, it just moves between system and surroundings. Now the two big words. Exothermic means energy exits the system. Think of combustion. The fuel's potential energy turns into kinetic energy of particles, and that energy flows out as heat, so the beaker gets hot. Endothermic is the opposite. Energy enters the system. Ice melting pulls heat from the surroundings to break bonds, so the beaker feels cold. The arrow always points the way the energy goes. Here's why this matters. If you know whether energy is leaving or entering the system, you instantly know what happens to the surroundings. Exothermic? The surroundings gain energy and get hot. Endothermic? The surroundings lose energy and get cold. And because energy is a conserved quantity, the amount the system loses is exactly what the surroundings gain, and vice versa. The universe's energy book always balances. A common mistake is saying cold enters the beaker when ice melts. That's not right. Cold isn't a thing that moves. Cold is just the feeling when heat leaves. So it's heat flowing out of the surroundings into the ice. Also, don't count the glass beaker as part of the system. It's part of the surroundings, even though it's touching the chemicals. The system is only the reacting stuff inside. So the whole idea is, pick your system, watch the energy arrow, and you'll always know who gets hot and who gets cold. If you try to measure the total heat inside a cup of coffee, you can't. It's impossible. Yet chemists predict exactly how hot a reaction will get every single time. They do it with a clever idea called enthalpy. We'll start with what enthalpy actually is, a way to track heat in a reaction. Then we'll see how breaking and making bonds acts like a seesaw of energy. After that, we'll work through a real example, and finally clear up a couple of mistakes that trip people up. Enthalpy, written as a capital H, is a measure of the total heat content of a system, like all the energy stored in the chemicals, when the pressure stays the same. But here's the catch, we can never measure that total H directly. It's like trying to count every grain of sand on a beach. What we can measure is the change in enthalpy, written as delta H. That change tells us how much heat the system absorbs or gives off during a reaction. If delta H is positive, the system took in heat from the surroundings. That's endothermic. If it's negative, the system released heat, exothermic. So enthalpy is our bookkeeper for heat flow. Think of a chemical reaction as rearranging atoms. To pull atoms apart, you have to break their bonds, and that takes energy, like stretching a spring until it snaps. That energy input is a positive change in enthalpy. But when atoms snap together into new bonds, they release energy, like the spring relaxing back. That's a negative change. The overall delta H for the reaction is the balance between these two, the energy you put into break bonds minus the energy you get out from making new ones. Imagine a seesaw. On one side sits bond breaking, pushing the enthalpy up. On the other side sits bond forming, pulling it down. Whichever side is heavier decides whether the reaction feels hot or cold. Let's calculate the enthalpy change for burning methane, natural gas. The reaction is CH4 plus 2O2 gives CO2 plus 2H2O. First, we break all the bonds in the reactants, for carbon-hydrogen bonds and 2 oxygen-oxygen double bonds. Using average bond energies, that's 4 times 413 kilojoules per mole plus 2 times 498, giving a total energy input of 2,648 kilojoules. Then we form new bonds in the products, 2 carbon-oxygen double bonds and 4 oxygen-hydrogen bonds. That releases 2 times 799 plus 4 times 467, which is 3,466 kilojoules. The overall delta H is the energy in minus the energy out, 2,648 minus 3,466 equals negative 818 kilojoules per mole. The negative sign means the reaction is exothermic, it gives off heat, which is why a gas flame feels hot. A common mix-up is thinking a positive delta H means the reaction feels cold, and a negative delta H means it feels hot. That's not quite right. The sign tells you the direction of heat flow from the system's point of view. A positive delta H means the system absorbed heat, so the surroundings lose heat and feel colder. An ice pack getting cold is endothermic, it takes heat from your skin. A negative delta H means the system released heat, so the surroundings gain heat and feel warmer. A campfire is exothermic, it gives heat to the air around it. So the sign is about where the heat goes, not just the temperature you feel. The whole idea is, enthalpy change is the net heat flow at constant pressure, and its sign tells you whether the system is a heat sponge or a heat source. A tidy room never tidies itself, but it will always get messy on its own. That one-way street is a fundamental law of the universe. It's not about laziness, it's about something deeper, something that drives everything from a cup of tea cooling down to a star burning out. We're going to unpack this one-way street. First, we'll define what entropy actually is. It's more than just a messiness. Then we'll look at how it works, using the idea of probability. We'll do a worked example, calculating the entropy change when a solid dissolves. And finally, we'll clear up the biggest mistake people make about the second law. Entropy, given the symbol S, is a measure of disorder. But a better, more precise way to think about it is this: it's the number of ways energy can be spread out among the tiny particles in a system. Imagine a perfectly tidy room. There's really only one way for every single book, sock, and pencil to be in its exact, designated spot. That's a low entropy state. Now, a messy room has countless arrangements. The sock could be on the lamp, the book under the bed. That's a high entropy state, with energy and matter distributed in many more possible ways. Here's the statistical heart of it. If things move and change randomly, like molecules constantly jiggling and bumping, they are overwhelmingly more likely to end up in a messy, high entropy state, simply because there are so many more messy arrangements than tidy ones. It's like shaking a box with a single red marble in one corner. After a shake, the marble could be anywhere. The one at IDO corner is just one possibility out of millions. This leads to the second law of thermodynamics. In any spontaneous process, the total entropy of the universe always increases. The universe, as a whole, is on a one-way trip toward greater disorder. Let's make this concrete. Imagine a crystal of table salt, sodium chloride, sitting in water. In the solid crystal, the sodium and chloride ions are locked into a rigid, orderly lattice. There's only one arrangement. When it dissolves, those ions break free and spread throughout the entire volume of water. Now, each ion could be in a vast number of different positions. The number of possible ways to arrange the ions has exploded. This massive increase in possible arrangements means the entropy of the system has gone up. We say the entropy change, delta S, is positive. The dissolving process is spontaneous partly because it leads to this huge increase in disorder. The biggest mistake is thinking the second law says entropy must always increase in the system you're looking at. It doesn't. It says the total entropy of the universe, the system plus the surroundings, must increase. This is crucial. A growing plant looks like it's creating order from disorder, building complex structures. But to do that, it takes in energy from the sun. The sun is pouring out vast amounts of energy, becoming more disordered in the process. The plant's local increase in order is more than paid for by a much larger increase in disorder in its surroundings. So the whole idea is, the universe's total entropy always marches upward, even if small pockets can become more ordered along the way. Why does ice melt only above 0 degrees Celsius, even though melting always increases disorder? Because temperature itself can flip a switch on what's possible. A reaction that won't happen in the cold can become spontaneous just by warming it up. We're going to meet the master equation that settles the argument between enthalpy and entropy. We'll see what Gibbs free energy is, how it works like a balance scale, the two cases where temperature flips the sign, and why this single idea is so powerful for predicting any reaction. Gibbs free energy, written as delta G, is a single quantity that combines the enthalpy change and the entropy change of a process. The formula is delta G equals delta H minus T delta S. Here, T is the absolute temperature in Kelvin. The sign of delta G is the true test of spontaneity. If delta G is negative, the process happens on its own. If it's positive, the process won't go without outside help. It's like a final score that tells you which way nature will move. Think of the equation as a balance scale. On one side sits the enthalpy change, delta H. On the other side sits the entropy change multiplied by temperature, T delta S. The temperature acts like a volume knob on the entropy term. At low temperatures, T delta S is small, so delta H dominates. But as you turn up the heat, T delta S grows larger and larger. If it grows big enough, it can outweigh a positive delta H, flipping the sign of delta G from positive to negative. The scale tips the other way. Let's walk through the melting of ice as a concrete example. Melting takes in heat, so delta H is positive, about 6 kilojoules per mole. But liquid water is more disordered than ice, so delta S is also positive. Below 0 Celsius, the temperature is low, so T delta S is small. The positive delta H wins, making delta G positive. Ice stays frozen. Above 0 Celsius, the temperature is high enough that T delta S becomes larger than delta H. Now delta G is negative, and the ice melts spontaneously. The exact tipping point is 0 degrees, where delta G equals 0. Without Gibbs free energy, enthalpy and entropy often give contradictory signals. A process might be favored by entropy but opposed by enthalpy, leaving you stuck. Delta G resolves the contradiction into a single, actionable prediction. It tells you, for any reaction at any temperature, whether the universe as a whole will allow it to happen. So the whole idea is, Gibbs free energy is the ultimate decider of spontaneity, turning a tug-of-war into a simple yes or no. Why does wood sit in air for years without burning, but burst into flames the moment you touch a match to it? The answer is an invisible hill that every reaction must climb. Even though burning wood releases a huge amount of energy and is totally spontaneous, the molecules are stuck. They need a push to get over that hill before they can tumble down the other side and release all that heat. We're going to climb that invisible hill together. First, we'll see what this barrier really is. It's called activation energy. Then we'll look inside a crowd of molecules to understand why only a few of them ever make it over the top. After that, we'll meet the clever trick that nature and engineers use to speed things up, a catalyst that digs a tunnel right through the hill. And finally, we'll see this in action inside your own body and in every car on the road. Think of a ball sitting in a small dip at the top of a bigger hill. To get it rolling all the way down into the deep valley below, you first have to push it up and over that little bump. That bump is the activation energy. In a chemical reaction, molecules are like that ball. They're full of potential energy, but they're stuck in their current shape. To transform into products, they first have to smash together hard enough to break their existing bonds, and that takes a minimum amount of energy. We call that minimum the activation energy, or EA. It's the entry fee for the reaction. Now, not every molecule in your wood is moving at the same speed. In any sample, there's a whole spread of kinetic energies. Some are slow, some are fast, most are somewhere in the middle. This spread is called the Maxwell-Boltzmann distribution. Picture it as a lopsided bell curve. The activation energy is a vertical line drawn on the right-hand side. Only the molecules in the tail of the curve, the really fast ones, have enough energy to get over that hill. If the hill is very tall, the line moves further right, and the number of molecules that can react shrinks dramatically. That's why wood doesn't just burst into flame at room temperature. Almost no molecules have the energy to start the reaction. So how do we speed things up without just making everything hotter? We find a shortcut. Imagine our ball and hill again. Normally, the ball has to go all the way up and over the peak. That's the uncatalyzed reaction. Now imagine someone digs a tunnel straight through the hill, much lower down. The ball can roll through that tunnel instead. The start point and the end point haven't moved. The overall energy change, the delta G we learned about, is exactly the same. But the barrier is now much smaller. That tunnel is a catalyst. It provides an alternative path with a lower activation energy, so many more molecules can make the journey, and the reaction happens much faster. And the catalyst itself? It emerges completely unchanged, ready to help the next ball through. This isn't just a lab trick, it's happening inside you right now. Your cells produce hydrogen peroxide, which is toxic. An enzyme called catalase acts as a catalyst, lowering the activation energy so the peroxide breaks down into harmless water and oxygen millions of times faster than it would on its own. The catalase itself is unchanged after the reaction. In your car, a catalytic converter uses metals like platinum and rhodium to carve similar tunnels for nasty exhaust gases like nitrogen oxides. It helps them react to form harmless nitrogen and oxygen before they leave the tailpipe. So the whole idea is this: a catalyst is a shortcut that leaves the destination unchanged, but makes the journey possible for almost everyone. Your body right now is running on the same fundamental energy rules as a burning campfire. Both are breaking down fuel and releasing energy. So how does a sandwich power your thoughts without setting you on fire? The answer is the energy story, a universal set of rules that governs everything from a battery to a leaf to your own muscles. We're going to see how the energy story plays out in 3 real-world systems: a battery, a leaf doing photosynthesis, and your own cells doing respiration. We'll look at the 2 directions energy can flow, storing it up or letting it out, and clear up a big mistake people make about burning calories. By the end, you'll see that a campfire and your breakfast are just 2 chapters of the same book. The energy story is simply the universal tracking of energy as it moves into, out of, and within any system. Think of it like a bank statement for energy. Whether the system is a battery, a leaf, or a muscle, the rules are exactly the same. Energy is never created or destroyed, it only changes form or moves somewhere else. That's the first law of thermodynamics in action, and it's the foundation of every energy story we'll look at. Let's see this in 3 systems side by side. A battery converts stored chemical energy into electrical energy. That's what powers your phone. A leaf captures light energy from the sun and uses it to build glucose, a sugar molecule packed with potential energy. This is an endothermic process because it absorbs energy. Then, in your cells, cellular respiration breaks that glucose back down to release energy, storing it in a molecule called ATP. This is exothermic. It releases energy, just like a campfire, but in a controlled, step-by-step way. The energy story always has 2 directions. Endothermic processes store energy. Photosynthesis is a perfect example. A leaf takes in low-energy carbon dioxide and water, adds sunlight, and builds high-energy glucose. Charging a battery is the same idea. You push energy in to store it. Exothermic processes release energy. Cellular respiration breaks glucose to release ATP, a discharging battery powers a device, and a campfire releases heat and light. The key is that the total energy of the universe never changes, it just moves between being stored and being released. A big mistake is thinking burning calories is just a metaphor. It's not. When you exercise, your cells are literally breaking the same chemical bonds in glucose that a fire would break, releasing the same amount of energy. The difference is your body does it through many small, enzyme-controlled steps, capturing the energy as ATP instead of letting it all out as heat at once. Another mistake is thinking energy is created in any of these systems. It never is. In a battery, in a leaf, in your body, energy is only ever transferred from one place to another or transformed from one type to another. The whole energy story is about following that journey. You've just walked a path from a single spark of energy to the blueprint of every reaction in the universe, but if you can't see how it all connects, you're left with formulas, not understanding. Think of a campfire. A tiny match sets a log ablaze, releasing heat and light, and the solid wood vanishes into smoke and ash. That one event holds the entire story of energy, disorder, and the hidden hurdle every reaction must clear. This video weaves together everything we've learned into one clear narrative, the one energy story. We'll first define what this story is, then walk through its 4 chapters: conservation, entropy, spontaneity, and activation, using a single, familiar example, a burning candle. Finally, we'll see it all on one unified energy landscape that shows energy transforming but never disappearing. The one energy story is the unified narrative that connects every piece we've learned into a single, inevitable logic for all change. It says, the total energy of the universe never changes, that's the first law. But that energy always spreads out and becomes less useful, increasing entropy, as the second law demands. Whether a reaction happens on its own, its spontaneity, is decided by the tug-of-war between enthalpy and entropy at a given temperature, captured by Gibbs free energy. And even when a reaction is spontaneous, it still needs a kick of activation energy to get started. These 4 ideas aren't separate rules, they're chapters of the same story. Let's walk through the 4 chapters. Chapter 1, total energy is conserved, but it degrades from concentrated forms, like chemical bonds, into dispersed heat. Chapter 2, entropy measures the dispersal. Reactions tend toward states where energy and matter are more spread out and disordered. Chapter 3, Gibbs free energy combines these 2 forces. Delta G equals delta H minus T delta S. If delta G is negative, the dispersal drive wins and the reaction is spontaneous. Chapter 4, even a spontaneous reaction faces an activation energy barrier, a hill it must climb before it can roll down to products. That's why a match is needed to light a candle, even though the wax wants to burn. A burning candle traces the full story perfectly. The wax is a store of chemical potential energy. When it reacts with oxygen, that energy is conserved, it transforms into heat and light, warming the room. At the same time, the orderly solid wax molecules become dispersed carbon dioxide and water vapor gases, entropy shoots up. This reaction is spontaneous at room temperature, the Gibbs free energy change is negative. But you still need a match. The flame provides the activation energy, pushing the wax molecules over their initial energy barrier. Once over the hump, the reaction cascades downhill, releasing far more energy than the match put in. Now let's see it all on one energy landscape. Picture a graph with energy on the vertical axis and the reaction path on the horizontal. On the left, the reactants sit at a high energy level, they're the wax and oxygen, full of stored potential. A hill rises in front of them, the activation barrier. Once they're pushed over that hump by a match, they slide down a steep slope to the right, ending as products at a much lower energy. Arrows show the energy difference dispersing into the surroundings as heat, never lost, only spread out. This single picture unites conservation, entropy, spontaneity, and activation into one story. Energy flows downhill, but it always needs a push to start.